Okay, there are two main things we need to get accomplished today. The first one is we need to review the computer output and some of the interpretations from linear regression. I will give you a list of everything that you need to be able to identify and everything that you need to be able to interpret. Also, we are learning a new panic and phantoms. The good news is that this panic and phantoms that we're going to learn, I'm not going to take you through the entire panic or phantoms procedure. I'm going to take you through the assumptions and the calculation, and that's it. The likelihood that it comes up on the AP test is very small. And if it does come up, it's probably just going to be the calculations. So it's not worth our time to do the entire procedure. That work for us? What? No. Okay. So, question of interest is at the top. We're not going to answer this question just yet. When we do the panic and phantoms, we will. But just so you know what the data represents, our question is, does there appear to be a useful linear relationship between question number and percent correct? So what this data shows, 1997 was the first year the AP Stats test was given. This data shows on the x-axis is the question number for the multiple choice. There were 40 multiple choice. On the y-axis is the percentage of students that answered that question correctly. So question number versus percentage of students that answered that question correctly. So we want to know, is there support for the test fatigue theory? That theory says the thought that later questions are answered correctly less often because test takers are weary from taking the test. Now, looking at our scatter plot, does it look like there's evidence for the test fatigue theory? Yeah, for sure. Why? It's a negative slope. Yeah, it's a negative slope. If I were to ask you to interpret that scatter plot, what would you talk about? What's the F FUDs? Okay, what does F stand for? Form. U. Unusual. D. Direction. S. Strength. So we would say something like there is a moderate negative linear relationship between question number and percent correct. In terms of unusual, maybe that point is unusual. That's about it. FUDs you only use when it's bivariate numeric data, a scatter plot. What do you use if it's univariate numeric data, like a histogram, a dot plot, a box plot? CSSU. What do you use for categorical data, like a bar chart? Compare. Okay, here's what you need to be able to find. One type of output just gives you the regression equation right at the top. Oftentimes, it's not going to give you that, or if it is, I'm going to black it out so you can't see that part, and I'm going to make you read this part instead. Here's why that part is important to you. Question number, that's our x. So this number then is the coefficient on x, in other words, the slope. The number that is next to the constant is the y-intercept. You need to be able to interpret both of those. When interpreting, what is most important is that you include the word predict. Predict. Do we want to go through those sentences, or are you confident that you can interpret slope and y-intercept? Yeah, we want to go over both. Okay, slope. Remember, is change in y over change in x, which in our case is negative 0.9317 over 1. Y is the percentage of students that answered that question correctly. X is the question number. So if I'm going to interpret that, I'm going to say when the question number increases by 1, the percentage of students answering that question correctly is predicted to decrease by 0.9317%. Very important that you write the word predicted. Very important that we say decrease because it's a negative slope. And very important that you provide units, which in this case is percent. I'm not going to do the y-intercept. The y-intercept is the predicted y when x is 0. So for question number 0, we predict 84.855% of students to answer that question correctly. Good so far? Okay. Next things we have to be able to identify. R squared. Remember, R squared adjusted you don't use. What is the term for R squared? Coefficient of determination. Sorry if someone else said that. It's kind of hard to hear you all. Okay, so that's the coefficient of determination. The correlation coefficient is R. How would I find R in this case? Take the square root. So I just take the square root of 0.41. That's it? Got to remember positive and negative. In this case, is R going to be positive or negative? Negative. Negative slope, so R will be negative. Okay. Next thing we have to be able to identify this number right here, this S, or sometimes it's written as SE. That is the standard error of the residuals. Standard error. Okay, last thing that I don't think we talked about in Chapter 5, but you're going to need now. In Chapter 5, we didn't look at these two standard deviation numbers, the ones I just boxed. That is the standard deviation of the y-intercept and the standard deviation of the slope. Of the two numbers, which one is more helpful to us? Not standard deviation. Which is more helpful to us, y-intercept or slope? Slope, for sure slope. Any of the numbers that have to do with y-intercept, you're pretty much not going to use. But the numbers that have to do with slope, you are. So that 0.1944, that is the standard deviation of the slope. So that 0.1944 is the standard deviation of the slope. Okay. A few other things. From that analysis of variance, you don't need to know that. Unusual observations, you do. It tells us that R denotes an unusual observation with a large standardized residual. So you'll see R over here. First of all, what is a residual? Actual minus predicted. So you would calculate a residual for every single point, and it's the actual y subtract the predicted y. What do we call an observation that has a large residual? What is the term for that? So the actual and the predicted are very different.
Outlier.
An outlier? Yeah, so when it says unusual observation, it means that these are outliers. What is the other type of unusual observation when discussing a scatter plot besides an outlier? influential observation. Okay. Those are the things that we have to be able to identify. There are quite a few things we need to be able to interpret. So I'm going to say that next. Do we have any questions about what I have written up there? No? Okay. These error properties, we're just going to skip that right now. And I'm going to go all the way down here and tell us all the things that we need to review. So either terms that we need to know or things that we have to be able to interpret. First one is interpreting r squared, the coefficient of determination. R squared was 0.41, or 41%. This is that sentence I told you to memorize. Is it safe to assume you probably just want me to write down the sentence? Okay. I'm going to do it in context. Approximately 41% of the variability in percentage correct can be attributed to the approximately linear relationship between question number question number and percent correct. So you're probably thinking to yourself, cool, what does that even mean? What that means, 41% of the time, y is changing because x does. The other 59% of the time, y changes for some other reason. So 41% of the time, y changes because x does. Second thing we need to discuss, what the difference is between an outlier and an influential observation. So what is the difference?
Outlier refers to it's like very high above and below. Influential observations like horizontally to the left or right.
Good, thank you. Outlier is going to be very different in the x direction. An influential observation will be very different in the y. When we say influential observation, what does it influence? What does that point influence? Slope and or r. So if you remember, normally what we would do for an influential observation is calculate slope and r, remove the point, calculate slope and r again, and ask ourselves, did it change? Okay, let's see if we remember this term. Extrapolation. Extrapolation is when you use your equation to predict y for an x outside of the domain. Use your equation to predict y for an x outside of the domain. Why is that an issue?
Because you don't know if the trend.
We don't know if the trend continues outside of our domain. Okay, last thing we need to talk about, and that is the difference between SE and S sub B. We need to be able to find both, bless you, and we need to be able to interpret both. SE is the standard deviation of the residuals. So it's how much variability there is in the residuals. Next thing I'm going to write down is the interpretation of SE in context. SE has to do with the residuals, so it has everything to do with the y direction, nothing to do with x. So here would be the interpretation. We estimate that observations in percent correct will typically deviate from the regression line by 11.62 percentage points. So it's the average deviation in the y direction. Again, has nothing to do with x, only y. Okay. So then S with a little b, so this is standard deviation of the slope. This one I'm going to give you the definition in general, just in general. So this is the typical deviation of little b. Little b is sample slope from its mean value, which is beta. Okay. This one, in my opinion, is hardest to understand. What S little b represents, or how you would find it, is if you took a whole bunch of samples and you calculated the sample slope for all of those samples, then you took the standard deviation. So that is a measurement from many samples, not just one sample. It's a measurement from many samples, not just one sample. If we took a whole bunch of samples, found all of their sample slopes, and then calculated the standard deviation. It's a measurement of about how far the sample slope would be from the population slope. Whereas SE is for one sample. Okay. All of that was review. None of that was new. Questions from me? Okay, at this point, go to your copy of this. We're going to start fresh, and now we're actually going to answer this question of interest. Before we jump into the hypothesis test, I want to tell you what the assumptions are. These assumptions are very different than any of the other assumptions that we have done. So this is where I want you to look at the errors figure. So first thing for you to know, when I say errors, that's just another term for the residuals. So the assumptions have to do with the residuals. There are 4 assumptions that you will check, always referring to the errors or the residuals. The first one, the first property or assumption that you are going to check is that the errors have a mean of 0. Okay, how are you going to check that? You are going to look at a dot plot or a histogram. of the errors. You will not be asked to construct this yourself. You will be given a dot plot or a histogram of the errors. The next assumption or property is that the errors have a constant standard deviation. To check that, you would have to look at a residual plot. So if you remember, a residual plot plots x versus its residuals, or x versus all the x's residuals. What are you looking for in a residual plot? What indicates that a linear model is a good fit? No pattern. What pattern is in particular an issue? A curve. What else? There's another type of pattern that we looked for. Fan. A fan. In particular, we want to make sure that there is no fan pattern. Fan pattern is when the points start out close together, but then they fan out. That would tell us that the standard deviation is not constant. Third property or assumption is that the errors are normally distributed. To check this, you're going to look at a dot plot or a histogram. And again, I would give this to you. You're not going to construct it yourself. Do you remember the other plot that is specifically whether or not a distribution is normal? Normal probability plot. I will tell you in your homework, you do have one question where you are constructing a normal probability plot. You're going to do it on the calculator. I will tell you what question it is so that we can review how to do that. If you had a dot plot or a histogram, you're just going to eyeball, does this look like it's a normal distribution? What is the first assumption that we normally always check? Random. So it's not quite one of the assumptions. Instead, the errors have to be independent. So the residual for one x value is independent of the residual for the next value. This one we just assumed to be true. So those are the four assumptions that you would check. I have not given you any graphs, so we are not checking these assumptions for our data. On the AP test, you would never have to construct the graph yourself. You would be given the graph and you just would need to look through and determine, does it look like these are reasonable? Those are the assumptions. You do have a question or two in your homework where you're going to need to check these assumptions. Okay, let's get to the calculation part. So looking at our question of interest. Does there appear to be a useful linear relationship? Is there support for the test fatigue theory? We're not going to go through the entire panic or phantoms. What I do want to go over, though, is the parameter and writing the null and the alternative, because we're going to need that for the test statistic. In this case, if you were going to do the full phantoms, the parameter we are looking at is beta. Beta is population slope. So in our case, beta is going to be the population slope between question number and percent correct. Again, percentage of students that answered that question correctly. Your null, 99.9% of the time, you are assuming that the population slope is 0. Slope of 0 is a horizontal line. That means there's no useful relationship. If we were answering the first question, does there appear to be a useful linear relationship? that would mean that our alternative is that beta is not equal to 0. Slope is non-zero, could be positive or negative. The second one is their support for the test fatigue theory, the thought that later questions are answered correctly less often because test takers are weary. We talked about, yes, it looks like there's evidence because there's a negative slope. In that case, the alternative would be that beta is less than 0. So these are two different questions, two different alternatives. Okay. We are going to answer this second question. Nah, I lied. We're going to answer the first one. We're going to answer the first one because in all likelihood, that's what you'll be asked on the AP test if you were to see this question. You would check those 4 assumptions that we just wrote. We're not actually going to do that. We're just going to jump right into the test statistic. So if we jump right into the test statistic, here is your formula. You are going to take the sample slope, subtract the population slope, and divide by standard deviation of the slope. Little b, we already looked at, this number right here. So that's the negative 0.9317. Population slope comes from the null, so that's 0. Standard deviation of the slope is 0.1944. And I will tell you that that number ends up being negative 4.79. Okay. T is defined by degrees of freedom. This is the only degrees of freedom that has a different formula. This degrees of freedom is n minus 2. N minus 2. There are 35 points or 35 questions in that figure. So in our case, it would be 33 degrees of freedom. So what we would do then is we have a two-tailed test. So we would find the probability that t is less than or equal to negative 4.79, but then multiply by 2, so it's a two-tailed test. And if you trust me, I'll tell you it's about 0. How would you calculate that in the calculator? What? TCDF? TCDF? Okay. A few things I want to point out to you. These are really important. Did you notice that this negative 4.79 shows up in the output? So you can really just take it right out of the output. Also, besides that, p-value, also in the output. Now, that p-value is a two-tailed test unless you're told otherwise. Other thing that's in the output that's also fun is degrees of freedom. It's this number right here. What I would like to point out, sometimes students get confused with this number. That 34 is the total degrees of freedom, not the total sample size. So that is not n. That 34 is actually n minus 1. So you should know how to use this formula, but if you forget, the test statistic is right in the output. Our case, we're rejecting the null. What does that tell us? Okay, I hear a lot of mumbling. We believe there is a linear relationship of some type between question number and percentage of students that answered the question correctly. Because remember, we did the one that's circled. So we have evidence to believe beta is not 0. So then a lot of times in real life what happens, if we say beta is not 0, we're going to follow it up with a confidence interval so we can get an estimate of beta, an estimate of the slope. Questions on this before I show you the confidence interval formula?
What are the assumptions for a test for confidence?
The 4 that we wrote down by the figure.
Just those, okay.
Yep. Ela?
And this test will always be a two-tailed test unless it's otherwise?
Yes. Yeah. It's kind of like a matched pairs one where 99% of the time it's going to be one way.
Okay.
Most of the time, all we care about is there a linear relationship of some type? You could be asked a question like the second one that refers to a specific slope being positive or negative. Most of the time, it's two-tailed, though. Not all the time, though. You guys got that? Not all the time is it two-tailed, just a lot of times it is. Okay. This next part is going to take like 2 minutes, and then we're done with notes. Maybe 4. Give me 4 minutes. Okay. If we're going to do a confidence interval, sample slope plus or minus t times standard deviation of the slope. So that's the part that I think is hardest to remember, so you're not dividing by root n. So our sample slope, we already got, it's at negative 0.9317. T, we would look up in the table with 33 degrees of freedom like we did above. Are you okay if I just tell you what it is? Yep, great. Ends up being 2.04. That sample slope we got above, 0.1944. So our confidence interval ends up being 1.329, comma, negative 0.5354. So that ends up being the confidence interval. And you interpret it like you would any other confidence interval. Okay, if I asked us the second question, is there support for the test fatigue theory based on this confidence interval? What would you say? Yes, because the entire interval is negative. The entire interval is negative, so we have evidence to believe there's a negative relationship between question number and percentage answered correctly. Like I said, theoretically on the AP test, you could be asked for the full phantoms. I would be shocked if that were the case, though. If this comes up at all, you're probably going to be doing something that we just did, just the calculations. Questions for me?